Hello GCT Chemistry class. In this video we are going to be covering the next section of Module 13, which includes pages 454 to 465 in your hardcover book. And we'll be going over examples 13.2 and 13.3, and on your own 13.2 through 13.5. So we will get started here by looking at how to determine the delta H of a chemical reaction using bond energies, and I'm starting on page 454. And so one interesting and very visual way of observing the breaking and formation of bonds is by creating Lewis dot diagrams. So looking at this equation here, we have the combustion of methane. So we have CH4. When it's reacted with oxygen, it's producing carbon dioxide and water. And then if we were then to visualize the bonds between these elements, we can see the carbon with the 4 hydrogens around it, the 2 double oxygens, and then also forming the carbon with the 2 oxygens around that, the CO2, and the 2 water molecules. So it's a nice way for us to see all the bonds in that reaction. And we know that energy is required to break the bonds. That's on this reactant side. We have to break all these bonds. And energy is released when the bonds are formed on the product side. And it's all sort of summarized in this equation for determining the delta H, that the energy required to break the bonds can subtracted by the energy released when the bonds are formed will then provide us with the delta H for a reaction. So on page 456 you have a nice table that includes the value of the bond energies between various chemicals. So for example, this is the carbon-hydrogen bond, and it's been quantitated here. Our units are kilojoules per mole for this particular chart, but in other charts it could be offered in kilocalories per mole. And we're given this numerical value for that bond, which will help us in some future problems. So let's look at sort of reviewing this concept of delta H in exothermic versus endothermic. And just to review that equation we just looked at in the previous slide, that delta H, energy required to break bonds minus energy released when bonds are formed, that mathematical formula can help us arrive at the delta H. Now we remember from the beginning of the module, if a reaction is exothermic, the delta H is negative. So when applying it to this mathematical formula, that would mean that this energy here is less than this energy here, because that would provide us with a negative number. The endothermic reactions, however, this energy here is greater than this energy here, and that's how we arrive at a positive delta H. All right, now let's look at example 3.2 in your book. I am just checking the page number, and we are on 457. And so the problem starts off like this. It says, to make ammonia, which is NH3, nitrogen and hydrogen are reacted at a high temperature according to this equation. The equation's provided at the top. What's the delta H for this reaction? Is it endothermic or exothermic? So the first strategy we're going to use for this is to create Lewis dot diagrams, and we can see for the diatomic nitrogen molecule, it has a triple bond connecting the two nitrogen atoms. And then for the hydrogens, we have 3 molecules of 2 hydrogens bonded together. And then our products here are each NH3. There's 2 molecules of the ammonia atoms. So now we're going to use this information to calculate our delta H. So we can use this table of bond energies that we referenced before, and from that we can look for some of the bonds that were provided here. So we want to find the N triple nitrogen bond and the hydrogen bond, and then the nitrogen hydrogen bond. And you can look here on the table, we have the triple hydrogen bond and the nitrogen hydrogen bond, and then the double hydrogen bond. And we can use those numerical values. I've summarized it here on this table. We find the exact kilojoules per mole for each one of those bonds. And then we can go back to our equation, which is listed here, the N2, H2, NH3. And we use these stoichiometric coefficients to help us determine how much to multiply those mathematical values from the table, what to multiply those by. So we have 1 nitrogen diatomic molecule here, and this is the 942 kilojoules. Here we have 3 of the hydrogens. And then in this case, we have in the NH3, each NH3 has 3 NH bonds, but since there's 2 of them, there's a total of 6 of those bonds in these 2 molecules. So then we multiply that by the 386, and this would be one value that you've added together, subtracting this value here, and you'll get a negative 78 kilojoules per mole. So that is one example of how to tackle the delta H in that. Now we are going to take a look at another example, and I'm just pulling this down. Okay. It says the complete combustion of methyl alcohol, which is CH3OH, is used to power some experimental automobiles. What is the delta H of that reaction? So first we create the equation. Again, this is a combustion, so it's reacting with oxygen, and our products would be carbon dioxide and water. Then the equation needs to be balanced, so we've added in the proper stoichiometric coefficients. And then you can create the Lewis dot diagram based on these, on this equation. And then you can see a complex number of bonds formed between the different atoms. Using this diagram then, you can reference this chart again that I mentioned here with these different bond energies, and then carefully record the different amounts of the different numbers of each bond and multiply it by the bond energy for each one. So for example here, for the CH bond, the carbon hydrogen, we count on the reactant side, we have 6 of those. 1, 2, 3, 4, 5, 6. So we multiply 6 times the value for that one bond, the 411 kilojoules per mole, and then that would provide the bond energy for those. Then you can move to the 2 mole, the 2 times the carbon oxygen bond here, and that provides a value for those. Then you have another 2 for the oxygen to hydrogen bond here. And so you've carefully then accounted for all the bonds in these molecules. Then you would add 3 times, you have 3 oxygen, double oxygen with double bonds between them, and multiply the 3 by those here. And so now you've accounted for all the bonds in the reactants. Now notice how the sign changes to subtraction, because now you'll be accounting for the bonds in the product side. You have 4 times these double bonds for the carbon and the oxygen, so that's the 799 kilojoule. And then finally you have 8, you have 1, 2, 3, 4, 5, 6, 7, 8 of the oxygen times hydrogen, and then you get a value for this. So you'll have a value for all these subtracted by a value for all these, and you get the delta H. It's negative, and I can't remember if it asked, but that would definitely be exothermic because you have a negative value for the delta H. All right, now let's look at On Your Own 13.2. We're on page 460. And the question reads like this. Hydrochloric acid, which is HCl, is widely used as a cleaning agent in both home and industrial use. To make HCl, chemists react hydrogen gas and chlorine gas at high temperatures. What if the delta H of this process is it exothermic or endothermic? So we start with our equation here. The hydrogen plus the chlorine gas, they're both homonuclear diatomic molecules creating HCl. Then we need to balance the equation by adding a 2 to the product side. And then you create the Lewis dot diagrams for each one of these molecules. Then, again, you'd use the table that we referenced, this table here, to look up the specific bond energies. And so we would come up with this. We have 1, there's an imaginary 1 there, like 1 of these hydrogen to hydrogen bonds, 1 of the chlorine to chlorine, and then we would be those are all the reactants, then we'd be subtracting the products. It's 2 times the hydrogen chlorine bond, and then the answer for that is negative 80 kilojoules, and so that would be exothermic because we have a negative delta H. Okay, now let's look at On Your Own 13.3, a similar question. In the acetylene torch, it says C2H2, the acetylene is burned to make hot blue flame that cuts or welds metal. Assuming the combustion is complete, what's the delta H? So again, we're starting with the regular equation, but then it needs to be balanced, so we're adding these stoichiometric coefficients. Then we've created the Lewis dot diagrams for each one of the molecules, and then you would be referencing that table and looking at each one of these bonds, counting each one of the type of bonds, and multiplying the number of the bonds you have by the bond energy from the table. So you get a total for all the reactants, and then you subtract the total for all the products. In this case, we have negative 2,444 kilojoules. All right, moving ahead, page 460, we have Hess's law, which states that enthalpy is a state function. So the question is, exactly what is a state function? And so in the book it defines it as, or it describes it as any quantity that depends solely on the final destination, not on the way that we get to that destination. So in the example below that they have is that the water is the same molecule in two different reactions, even though the pathways for creating it are different. So here you have a formation reaction of hydrogen and oxygen to make the water. And then here you have a decomposition. You have hydrogen peroxide breaking down into water plus oxygen gas. And yet we still have these two water molecules, and they both have the same properties in terms of the energy that's stored in it. So on page 462, we go into a little more detail on describing this concept of the enthalpy of formation. So just to review, a formation reaction is a reaction that forms a substance from simpler components. All right, so this was a formation reaction. Again, the hydrogen and oxygen to make the water. And the enthalpy of formation, which I guess it's hard to tell with those red squiggly lines, but it's a delta H with a subscript of the F, is the delta H of a formation reaction. And it's important to note that in this chart, which summarizes standard enthalpies of popular molecules, okay, also measured in kilojoules per mole, these are all done at standard conditions, which is 25 degrees Celsius and 1 atmosphere. However, just to note, that's not quite the same as standard temperature pressure. Okay, so moving on to page 463, we have a summary equation that talks about the standard change in enthalpy. So we're going to be using a new Greek letter. It's called sigma. It's kind of like a zigzag line, and that stands, it's a symbol that stands for summation, like the sum of a number of values. So here we have the delta H at standard conditions equals the summation of the enthalpy of formation of products minus the summation of the enthalpy of formation of reactants. And it's very abstract, so I encourage you to stick with it because I think when we do a couple problems it will be more obvious. So just to point out, the standard enthalpy of formation of an element in its elemental form is 0. And just to clarify that, it says chemicals like calcium, sodium, potassium, iron, these all have the standard enthalpy of formation of equal to 0. But just to clarify, on atoms that are found as homonuclear diatomics, like H2, N2, O2, and Cl2, they also have this value of 0 in their diatomic form, but not in their singular form. All right, so let's look at an example here. All right, it's asking what is the delta H of the following reaction. So we have 2 times nitrogen monoxide plus oxygen gas yields 2 nitrogen dioxide. And they're asking, is it exothermic or endothermic? So this is actually pretty straightforward because in this case, we're going to start with our products. So we look at the NO2 back on this chart right here. You see the value for the delta H here is 33.2. And then you use that, you have 2 as your stoichiometric coefficient, so it's going to be 2 times the 33.2, and that's giving our value for the product. Then you're going to start working with the reactants, right? You have NO, nitrogen monoxide. We'll find that on the chart. It's right here, 90.3. And there's a 2 in front of that as a stoichiometric coefficient, so it's going to be 2 times 90.3, minus, now in this case, because O2 is its elemental state, that is just going to be 0 for that value. So this part of it ends up being 0, and it's can be more or less disregarded. All right, so our delta H then in this case was this value minus this value, and we have 114.2 kilojoules. Since it's negative, again, it's exothermic. All right, let's look at the second half of example 13.3. It says some gasoline companies put a small amount of liquid ethyl alcohol into their gasoline. What is the delta H for the combustion of this chemical? So again, a combustion reaction, we're reacting with oxygen and forming CO2 plus H2O. Now, we just simply access those values back on the table. We're going to need to know H2O, CO2, the O2, remember, would be 0, and then the C2H6O2. So I'm just going to look at one of them, but we'll start with the CO2 here, right? So we look back at the table, you find CO2, it's negative 394 kilojoules per mole. And since we had 2 of these, right, it's 2 times the negative 394. This would be the value for the CO2. Then we go to the water here. 3 times the value of the water minus 242. And now we've finished our products. Now we'll be subtracting the values from the reactant side. We have 1, right, times the value for the C2H6O, which is minus 278. And in addition, we'll be subtracting 3 times, well, actually, that's not true. The O2, again, is 0, so we don't even really have to worry about that. Then after all the math is done, our delta H is negative 1,236 kilojoules, which, again, would be exothermic. All right, we've got 2 more very similar problems. We're looking at On Your Own 13.4, page 465. It says, when you use a pocket cigarette lighter, hopefully not to light cigarettes, you are burning gaseous butane, which is C4H10. Assuming it is complete combustion, what's the delta H at standard conditions for this reaction? Do not use bond energies. As tempted as you are to solve this problem, use Hess's law. So here is our full equation that's all balanced. We're going to start with our products, right? And again, we look for CO2 here, and here we are, negative 394. So we have 8 molecules or moles times the 394, and that's the value for the CO2 here. Then we have 10 of the waters. You look the water up on here, and it is important to look at the state of the water. This is in gas because there's 2 different values here. One's for gas and one's for liquid, but we have minus 242 for the gas. So it's 10 times minus 242. That completes our products. Then minus, it's going to be 2 for the C4H10. You find that on the chart. It's minus 126. And then 13, well, again, this will be 0 because the O2 is 0, so that's negligible. Then our delta H works out to negative, I'm not sure, it's 5,320. I think that's what it is. Oh, I'm sorry. Yeah, you're right. It is 5.32 times 10 to the third, or 5,320 kilojoules. All right. So here is our last example for this part of the unit. It has On Your Own 3.5 on page 465. In order to make the shells that house and protect them, many shellfish take solid lime, which is calcium oxide, from the ocean floor and react it with gaseous carbon dioxide that has been exhaled by marine organisms. The resulting calcium carbonate is the major component of their shell. What's the delta H for this reaction? All right, so here we have our equation, CaO plus CO2, CaCO3. Our delta H, again, we're going to start with the product. So we find CaCO3 on our chart, which is here, negative 1207. There's an imaginary 1 here, so it's 1 times negative 1207. That completes our product side, minus, then we have 1 times the calcium oxide, negative 635, and then also minus 1, because there's an imaginary 1 here, times the carbon dioxide, which is right here, 394, right? And when we do all the math, we have negative 178 kilojoule. So I hope that's been helpful in understanding how to calculate delta H, and then we'll be looking at some other problems in our next video.